Earlier this week, I introduced you to this worksheet, and we did some reading and explanation in class. But if you weren't there for that, this first part of the video will be helpful for you. If you were there for that part of things, you probably could skip the first few minutes and head into the moment when I start in on the practice problems. But for those of you who did not get this, or for anyone who wants to review this information, the basic unit of energy that we when we refer to a basic unit, this is like the standard unit of energy. This is what is used in environmental science and chemistry and physics. That basic unit of energy is a joule. And everything else is built off of that concept. Other units that we can be familiar with: calories, kilojoules, British thermal units, and the therm. And all of the different equivalencies are listed here. Equivalencies, remember, are when two units are equal, just showing how those units would be equal to one another. And we use equivalencies to create unit factors when we are doing conversions. So whether you're set up like this guy here, where you might have a value given to you. Okay, so let's say this one is given. And if it's given in a fraction, that's great. You can use a unit factor, right? You can see that this, I just kind of set it up with unit and factor. But when you have an equivalency, you have two things that are equal. So something divided by itself is technically equal. If you're just using unit factors to change from one form to another, you're not changing the value, but you would set them up as a multiplication problem with the particular factors, those equivalencies, across the way, and allow your units to guide your setup. So I call it mapping your units. Use your units to map out the problem. So this is something I always say about conversions. If you really focus on the units first, is going to help you solve those problems. And you might have a value that's not given to you in fraction form, and obviously you can still multiply that by unit factors. Let me finish this visual for you. And those can continue on until you reach the unit that is desired in the problem. So one of the things you have to do when you're reading through these word problems is really determine what unit you need to get to and what unit you are starting off with. And then from there, like what equivalencies are given to you, because oftentimes within the problem, the equivalencies are going to be given to you. All right, so back to this concept of energy. Energy is basically a measure of heat, but energy is given, or it's given to us in a unit that measures heat. But energy can come in a lot of different forms, and energy gets used when we are doing work. And the rate at which energy is used is called power. So power equals energy over time. And the unit that is used to talk about power is a little bit different because it is a derived unit, but it is one word where it's named after a scientist, and that is a watt. So you just need to know that within a watt, there is a rate of energy being used, and 1 watt is equal to 1 joule per second. Many of the problems you see in energy problems will deal with efficiency. A problem like this, like a 100 watt light bulb uses 100 joules per second of electrical energy. If it's 20% efficient, then the bulb converts 20% of the electrical energy into light and 80% is wasted. Like how much, what's the the amount of heat that is wasted? Let's say if we run that light bulb for 4 hours or something, you may get a problem like that, right? So where efficiency plays into it. So here's a little explanation on efficiency. And you have to understand there are two laws at work here. One is the first law of thermodynamics. Electrical energy can be transformed into light and heat energy. It can be transformed, like if it's captured properly, it can be transferred into other forms. But whenever energy is transferred from one form to another, we do lose the purity of that energy. So this is a law of conservation of energy. Obviously, that energy can't be created or destroyed. It's going to go somewhere, but it isn't captured efficiently necessarily. This means that the total amount of energy is going to remain the same. But what we do know is that order decreases, or we say increasing disorder, which is the law the second law of thermodynamics, that law of entropy is at work. So there's always going to be some kind of waste. And this states that the entropy of the universe increases with every physical process. Every change that occurs, you're going to be losing something in its usefulness. And so the measure of energy as heat is not a useful form. And one of the aspects of many of these energy problems is really analyzing the efficiency of different products or processes that are part of our everyday lives, and we're really dealing with humans and their use of energy. Okay, one of the other things that's going to help you in solving energy problems is being able to really kind of break down that problem and recognize what your given is and what you're actually being asked to answer in terms of your end product. So let's take a look at this question and we'll kind of pick it apart. How much energy in kilojoules does a 75-watt light bulb use when it is turned on for 25 minutes? So the first thing, I just want you to take a look at what you are asked. You're asking to go to kilojoules. You are told that you're using a 75-watt light bulb. And then you have this measured amount. So like this is your given right here, 25 minutes. My blue highlighter might not be that effective. So when I start off this problem, I'm actually going to start off with the 25 minutes because that's my measured amount. That's the one that's different from problem to problem because it could be like any amount of time, right? But I'm going to go 25 minutes. And then I'm going to start converting from one form to another. Now I know that watts is joules per second. So I'm going to take this to seconds. We'll start off by mapping our units out. Okay. So that's going to give me amount of time in seconds. I'm also going to take a look at the fact that this is a 75-watt light bulb. And so even though I know that it's 75 watt, I'm going to call it 75 joules per second because I know that 1 watt is equal to 1 joule per second. So I can just straight trade those out. And now I'm able to see that I'm going to be able to get to joules, which is a measure of energy. So right there, starting from time, and now I'm converting from time to energy. And then my next step really is to look at going from joules. So I know I need 1,000, that there are 1,000 joules in a kilojoule. And this is going to take me from my minutes to my energy and into the proper unit. So now I know that if this is the unit I'm looking for, this is my target unit, this is my measured amount, that I've gone through all of the steps of the conversion to get to that point. Well, obviously I need to put some numbers in here. So 1 minute is 60 seconds and really use that to map that out. Look, I'm going to double check. Those cancel, 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 cancel. And my unit that would be left would be kilojoules. And if I do the calculations, 25 times 75 times 60 divided by 1,000, I should end up with 112.5 kilojoules. And so the trick really is to read carefully and find out like what's our measured amount versus what's a conversion. And in this particular case, like when I've got this measured amount and then I know that I'm given a known rate that a particular piece of technology is actually using energy in there. So our conversions and our energy problems are often going to have something that's very defined, something that comes from the technology itself, and then you've got your target unit. All right, so for problem number 2, it gives us a kilowatt hour, and this has been well established, but we know that a kilowatt hour is a unit of energy. Notice that time is included in it, and that a kilowatt is the unit of power, and the hour is the unit of time. So if you can actually cancel them out, if you can like multiply out or factor out the time, then you would just be left with energy. And we know this one's energy, but I mean, like if you can get rid of the unit of time, then you should just be able to get down to kilojoules. So that's basically where we are. We're just transferring from one unit to another. This is the expression piece. So we can pull these apart And we are given here, or you could figure it out, that 1 hour is 3,600 seconds. So instead of putting an hour in there, let's go ahead and put seconds. And then instead of putting the watt, let's go ahead and put the joules per second. That'll cancel out those time units and just leave us with the joules, or kilojoules at this point. So 3,600 kilojoules just from playing with those units. And then one thing that I want you to know is that a kilowatt hour is 3,600 kilowatt seconds, or is the 3,600 kilowatt joules. And we are going to be asked about this. So we're just kind of setting up this equivalency for the next problem. It will help us solve the next problem. Number 3. So assume your electrical bill showed that you used 1,355 kilowatt hours over a 30-day period. Find the energy that is used for that 30-day period. So first of all, this is our given rate for this particular problem, right? So 1,355 kilowatt hours, and that is over a 30-day period. And we're going to leave that 30 days in there because it's asking us to figure it out for 30 days. So we just have to convert to kilowatt joules here. Well, our equivalency is set up here, and we could actually just take, and switch this out. We've got kilowatt hour, so we know that 1 kilowatt hour is equal to 3,600 kilojoules. And all right, so a little bit of math magic there. And obviously I was ready for this. So we've got 4,878,000,000 kilojoules for the 30 days. Or if you wanted to, you could actually write that as it does ask you about kilojoules, so you have to leave it in kilojoules, but you could write that as scientific notation. So 1, 2, 3, 4, 5, 6. Might make it a little bit easier to deal with later on. I don't know. Just sometimes makes it kind of a little neater. All right. There's that one.